Greetings and welcome to another Math Olympiad walkthrough. In this video, I'll be walking you through the Singapore Mathematical Olympiad for the year 2020, and this will be the senior section, round 1 paper. The Singapore Mathematical Olympiad is organized by the Singapore Mathematical Society. It comprises of 3 sections. Today, I'll be going through the senior section, which is for students with an age limit of 16 and under. There are 25 questions in total, comprising of 5 multiple choice questions and 20 open-ended questions. Students who score well will be invited to a second round. Starting with question 1, let b be a positive integer. If the minimum possible value of the quadratic function 5x squared plus bx plus 506 is 6, find the value of b. Pause the video here and give this question a good try. So question 1 is a completing the square problem. We can take the quadratic function given in its standard form and express it in the vertex form, which is 5 bracket x plus k squared plus 6. This is using the idea of completing the square. And we can take that vertex form and we can expand it. This will give us 5x squared plus 10kx plus 5k squared plus 6. Now we can compare the left-hand side and the right-hand side. So we can compare the constant terms. 506 must be the same as 5k squared plus 6. We can also compare the coefficients of x. So bx will be equals to 10kx. So first, comparing the constant terms, we are able to find the value of k to be 10. Then by substituting k equals to 10, b must be 10 times 10, which is 100. And that is our answer for question 1. Moving on to question 2. Express square root 5 plus root 3 plus square root 5 minus root 3 in the form of square root a plus b root c. Pause the video here and give this question a good try. Question 2 is pretty straightforward. Since we know that square root of a plus b root c is equals to the expression that we are given, we can remove the outermost square root by squaring both sides. So this will give us a plus b root c equals to, let's just call it a plus b squared. So when we expand it, we're going to get a squared plus b squared plus 2ab. This can be further simplified to give us 10 plus 2 times of root of 22. Now, what we want is not a plus b root c. What we want is square root of a plus b root c. So by square rooting both sides again, we'll get an answer of square root of 10 plus 2 root 22. Moving on to question 3. Simplify log base 8 of 5, open bracket, log base 5 of 3 plus log base 25 of 9 plus log base 125 of 27. Pause the video here and give this question a good try. So for question 3, this is a logarithm question. We're going to start by first simplifying the terms inside the bracket by changing them all to log base 5 using the change of base formula. So log base 25 of 9 will give us log base 5 of 9 divided by log base 5 of 25. Similarly, for log base 125 of 27, this will give us log base 5 of 27 over log base 5 of 125. Now we know that 9 is equals to 3 square, 25 is equals to 5 square, 27 is equals to 3 cubed, and 125 is equals to 5 cubed. So we can convert them all into powers. Then we'll use the power law to simplify it further. So we take out the powers. So for example, log base 5 of 3 square will become 2 log base 5 of 3. This is very nice because we can cancel the 2's on the numerator and denominator of the fraction as well as the 3's for the last term. We can also cancel the log base 5 of 5 because log base 5 of 5 is just 1. And by simplifying that, we'll get log base 8 of 5 times log base 5 of 3 plus log base 5 of 3 plus log base 5 of 3, which is just 3 log base 5 of 3. We can then change them to log base 2 convert them all to the same base, log base 2, using the change of base formula again. And this will help us cancel the log base 2 of 5 in the first numerator and the second fraction's denominator. This gives us 3 log base 2 of 3 divided by 3, because log base 2 of 8 is 3. 2 to the power of 3 gives us 8, so log base 2 of 8 is 3. The 3's will cancel, and our final answer is log base 2 of 3. Next, in question 4, let A equals to 50 to the power of 1 over 505, B equals to 10 to the power of 1 over 303, and C equals to 6 to the power of 1 over 202. We want to arrange A, B, and C in ascending order. So pause the video here and give this index question a good try. So to tackle this question, we need a strategy for inequalities of indices. And the idea behind this is that if I have two numbers A and B are both numbers bigger than 1, then if A is less than B, then if I raise both these numbers A and B to the same power n, A to the power of n would still be less than B to the power of n. So now I need to choose a number n to raise A, B, and C to the same power of. So that number is going to be 3030. And why have I chosen this number? This number is the lowest common multiple of 505, 303, and 202. So by raising A, B, and C to the power of 3030, I'll get 50 to the power of 6, 10 to the power of 10, and 6 to the power of 15 respectively. What I've done is that I've changed this question. So instead of comparing A, B, and C, I'm comparing 50 to the power of 6, 10 to the power of 10, and 6 to the power of 15 instead. So these numbers are easier to look at. They're still quite big, but they're easier to play around with. So if I can order these three numbers, I would have ordered A, B, and C as well. So let's start by comparing. Let's compare B against C. They look easy. So I have 10 to the power of 10 versus 6 to the power of 15. So I can take a fifth root on both sides. That will give me 10 squared times 6 cubed. 10 squared is 100. 6 cubed is 216. So between B and C, C is larger. So I can write down B is smaller than C. So let's compare A against B. I have 50 to the power of 6 versus 10 to the power of 10. Which one's bigger? So I can square root both sides. It will give me 50 cubed versus 10 to the power of 5. Now 50 cubed is the same as 5 cubed times 10 cubed. And 10 to the power of 5 is equal to 10 squared times 10 cubed. So I can cancel 10 cubed on both sides. So what I am doing is comparing 5 cubed against 10 squared. That is 125 versus 100. So A is more than B, or B is less than A. I was hoping for A is less than B, the problem would have been solved. But that was not the case. So unfortunately, we've got to do this one more time. We've got to compare A against C. So now I want to compare 50 to the power of 6 against 6 to the power of 15. So what I can do is I can take a cube root on both sides. This will give me 50 squared versus 6 to the power of 5. 50 squared is 2,500. 6 to the power of 5 is not that difficult to compute. By hand, you will get 7,776. This will tell us that A is less than C. Therefore, our final answer is B is less than A, which is less than C. Question number 5. Let P equals to log of sine x, Q equals to sine x to the power of 10, and R equals to 10 to the power of sine x, where x is between 0 and pi over 2. Arrange P, Q, and R in ascending order. Pause the video here and give this question a good try. So I'm going to tackle question 5 using graph sketching. But before I do that, I'm going to simplify these three graphs first. So instead of drawing y equals to log of sine x, I'm going to just draw y equals to log x. So basically, I'm going to ignore all the sine x in the p, q, and r functions. I'm just going to change it to log x, x to the power of 10, and 10 to the power of x. So changing all the sine x to x first. So if I sketch the first graph p, y equals to log x, it will give me this blue logarithmic graph that passes through the x-axis at the point 1. Next, for the graph for Q, this is a power law. So this is a power 10 function. So it will be this green graph here passing through the points 1, 1. Next, we have an exponential function shown here in red for 10 to the power of x. So this red line passes through the y-axis at 1. So let's now bring in the point that we have to do this for sine x to the power of 10 or 10 to the power of sine x and log of sine x. So how does sine x comes into play here? Now we know that x is between 0 and pi over 2. So sine x is between 0 and 1. So since sine x is going to be the same value for these blue, green, and red lines, and this number is going to be between 0 and 1, we can just draw an arbitrary vertical line anywhere between 0 and 1 and see where it passes through the red graph, the green graph, and the blue graph. So you can see that the red graph, where it intersects the vertical line, is higher than the green, and that would be higher than the blue point on the logarithmic graph. Therefore, the order will be P is the smallest, followed by Q, and the largest would be R. So P less than Q, less than R. Moving on to question 6. Find the minimum possible value of modulus x minus 10 minus modulus x minus 20 plus modulus of x minus 30, where x is a real number. Pause the video here and give this question a good try. Now to tackle question 6, we're going to draw a graph, and our key points will be at x equals to 10, 20, and 30, which are critical points where the graph changes. We're going to first sub in x equals to 10, and I'm going to walk you through modulus quickly because some of you may not be familiar with it since modulus has been removed from the AMATS syllabus recently. So firstly, we have modulus of 10 minus 10, which is modulus of 0, minus modulus of 10 minus 20, which is modulus of negative 10, plus modulus of 10 minus 30, which is modulus of negative 20. So what the modulus function does is that it turns anything negative inside into its positive counterpart. So negative 10 will become 10 and negative 20 will become positive 20. But 0 will remain unchanged because 0 is not negative. So this will give us a value of 10. So at x equals to 10, this function will give us a result of 10. At 20, when x is equals to 20, I can compute this, and this will give us a result of 20. So, and at x equals to 30, we get another point, which is also 10. So we can connect this graph. It will give us straight line graphs between the three crosses that we've found so far. And next, we have to consider x less than 10. When x is less than 10, the modulus of x minus 10 will be a negative number. So we have to flip it into negative of x minus 10. So negative x minus negative 10 is 10 minus x. Minus modulus of x minus 20. X minus 20 will also be negative, so that needs to be flipped as well. It becomes 20 minus x. X minus 30 will also be negative. It will become 30 minus x. If I simplify this, it will give me 20 minus x. So it will give me a blue line as shown on the left side of the graph. Similarly, for x greater than 30, I can do the same thing. In this case, when x is greater than 30, all the modulus functions will be acting on positive things. Because if x is greater than 30, something greater than 30 minus 10 would still be positive. So I can just remove all the modulus brackets, and I will just get a function x minus 20. So it will be a straight line graph with a positive gradient as shown on the right. So we can see that the minimum possible value is 10. Moving on to question 7. A parallelogram ABCD has sides AB equals to 39 cm and BC equals to 25 cm. Find the length of diagonal AC in cm if the diagonal BD is equals to 34 cm. Pause the video here and give this question a good try. tackle these kind of geometry questions, let's sketch what we know first. We know the parallelogram ABCD, the sides AB and the sides BC. We can also might as well label the other two sides. We also know the diagonal of BD. We can connect the triangle ABD, the three sides, and the angle theta, which is the included angle between sides AB and AD, using a formula known as the cosine rule. So cosine rule states that 34 square is equals to 25 square plus 39 square plus 2 times of 25 times 39 times cosine of the included angle theta. So that's one formula, but we're not going to calculate cosine theta. We don't have a calculator here. So what we can do next is we can look at another triangle. We're going to use the triangle with AC, the unknown diagonal, as one of the sides. So triangle ABC. And angle ABC is the interior angle, so it will be 180 degrees minus away theta, the previous included angle. So we can form another equation using cosine rule again. So now this time the unknown diagonal AC squared is equals to 25 square plus 39 square plus 2 times of 25 times 39 times cosine of 180 minus theta. Now this is pretty useful because cosine of 180 minus theta is a second quadrant angle, and we can relate this obtuse angle using the obtuse angle formulas for trigonometry. So cosine 180 minus theta is equals to negative cosine theta. So using a simple substitution, this is what we get. So the two equations that we have formed so far are very similar. And just nice, we can cancel away the cosine theta in both equations if we add these two equations together. So by adding both sides together, the left side will give me AC squared plus 34 squared, and the right side would be 2 times of 25 squared plus 39 squared. So bringing the 34 square over to the right-hand side, I'll get AC equals to square root of the whole thing, which is 2 times of 25 square plus 39 square minus 34 square, which is just 56. So that's our final answer. Moving on to question 8. Suppose we have sine of 45 degrees minus x to be equals to negative 1/3, where x is between 45 degrees and 90 degrees. Find the value of 6 sine x minus root 2 whole thing squared. Pause the video here and give this question a good try. So this question is a challenge of our knowledge of trigonometric properties. So the first thing we need to know is that sine 45 degrees minus x is going to be in the fourth quadrant because x is between 45 degrees and 90 degrees. So what we might want to do is first change it to a first quadrant angle, which is sine x minus 45 degrees. And what will happen is that the right-hand side will change from negative 1/3 to positive 1/3. This is because of the property that sine is an odd function, so sine of negative x is equals to negative sine x. Next, we can draw the reference triangle in the first quadrant, so we can draw a reference angle of x minus 45 degrees. And for this particular triangle, the opposite side will be 1 and the hypotenuse will be 3. Using Pythagoras' theorem, we can work out the adjacent side to be 2 root 2. This allows us to work out cosine x minus 45 degrees, which will be the adjacent side 2 root 2 divided by the hypotenuse of 3. Next, we're going to apply the addition angle formula to expand these two equations. So for sine x minus 45 degrees, we can expand this into sine x cosine 45 degrees minus cos x sine 45 degrees, which is equals to 1/3. For cosine x minus 45 degrees, we use the addition angle formula, and this will give us cosine x cosine 45 degrees plus sine x sine 45 degrees, which is equals to 2 root 2 over 3. And we're going to label these two equations, equation 1 and equation 2. So what we're going to do next is we're going to add these two equations together. So what will happen is that the cosine x cosine 45 degrees will cancel with the cosine x sine 45 degrees, because sine 45 is equals to cosine 45, which is equals to 1 over root 2. This is a special angle. Meanwhile, what will be left is sine x cosine 45 plus sine x sine 45, and both of these are also equals to 1 over root 2. That's why we will get 2 sine x times 1 over root 2 on the left-hand side. And on the right-hand side, we're going to get 1/3 plus 2 root 2 over 3. Next, what we can do is we can make sine x the subject. So if we make sine x the subject, we need to multiply by root 2 on both sides and divide by 2 on both sides. This will give us sine x equals to 1 plus 2 root 2 over 3 root 2. Now, in the question that we have, the question asks us to find the value of 6 sine x minus root 2. So we need 6 sine x. So we multiply by 6 on both sides. This will give us root 2 plus 4. But we want 6 sine x minus root 2, so we shift the root 2 over to the left-hand side. So 6 sine x minus root 2 is equals to 4. Now we just need to square both sides, and we will get 16. So that will be our final answer. Question number 9. If 8 cosine x minus 8 sine x equals to 3, find the value of 55 tangent x plus 55 divided by tangent x. Pause the video here and give this question a good try. Once again, question 9 is also a test of our trigonometric identities. Since the final expression is in the form of tangent x, so what we want to do is to create some tangent x. So we can divide the initial equation throughout by cosine x. This will give us 8 minus 8 tangent x, because sine x divided by cosine x is equals to tangent x. And on the right-hand side, 3 divided by cosine x is the same as 3 secant x. What we want to do next is to square both sides. This is because when we square secant, we can do something to secant square x, which we'll see later. So when we square both sides, what do we get? We'll get 64 plus 64 tangent square x minus 128 tangent x. This is just using the algebraic expansion of a plus b squared, or in this case, a minus b squared, which will give us a squared plus b squared minus 2ab. But on the right-hand side, 3 secant x squared will give us 9 secant square x. And we can use the Pythagorean identity here. It states that secant square x is equals to 1 plus tangent square x. So we'll get 9 plus 9 tangent square x. So what we want to do is to shift the 9 and the 9 tangent square x from the right-hand side over to the left-hand side. And we want to shift the 128 tangent x over to the right-hand side. So this will give us very nicely 55 plus 55 tangent square x equals to 128 tangent x. And if we divide throughout by tangent x, this will give us what we want. We will get 55 tangent x plus 55 over tangent x on the left-hand side, and 128 as our final answer. Question number 10. Find the number of ordered pairs x, y, where x, y are both integers, such that x squared plus y squared minus 20x minus 14y plus 140 is less than 0. Pause the video here and give this question a good try. So for question 10, what we need to do is first recognize that this inequality resembles the equation of a circle. So let's first rearrange this and see if we can find the center and the radius of the circle. So let's rearrange it. We get x squared minus 20x plus y squared minus 14y less than negative 140. So to complete the square for x and y, we can add 100 to the x terms, and we add 49 to the y terms, and we need to do the same for the right-hand side. So by completing the square, we'll get x minus 10 squared plus y minus 7 squared less than 3 squared. So this equation resembles a circle with center 10, 7 and a radius of 3. So essentially, finding the number of ordered points is like finding the number of points with integer coordinates that lie within a circle of with a center of 10, 7, but you're going to see later that the center really doesn't matter, but within a radius of 3. So let me draw this out to show you. So let's have a grid and we draw a circle with center 10, 7, but it doesn't really matter where the center is. And we have a red circle with radius 3. So what are the points that lie exactly on the vertices of this grid? So let's count these points. There's altogether 25 such points. So there will be 25 such ordered pairs. So that's our final answer. Question 11. The figure below shows a right-angled triangle ABC such that angle BAC is equals to 90 degrees, angle ABC is equals to 30 degrees, the length of line segment AB is 48 cm. Let P be a point on the side AB such that CP is the angle bisector of angle ACB, and Q is a point on side BC such that the line AQ is perpendicular to the line CP. Determine the length of the line segment PQ. So pause the video here and give this question a good try. So question 11 involves two major concepts, congruency and the trigo ratio of special angles. Now the first thing we can do is, since the sum of angles in a triangle is 180 degrees, that big yellow angle, angle ACB, must be equals to 60 degrees. And the two bisected angles, angle ACP and angle PCQ, must both be 30 degrees. We can also label the intersection of AQ and CP to be the point M. This allows us to state that the two triangles CMQ and CMA are both congruent. This is due to the ASA test. We have a common side CM with stated that CMQ is equals to angle CMA because all the angles are 90 degrees due to the two perpendicular sides. And angle MCQ is equals to angle MCA, the two yellow angles that we've shown earlier. Because the two triangles are congruent, we can also state that AC is equals to the length of CQ, and the two base sides AM is equals to MQ. And this is more important because this allows us to state that another pair of congruent triangles is triangle PMQ and triangle PMA. This is due to the SAS test. We have just shown earlier that AM equals to MQ, and we know that angle PMQ is equals to angle PMA equals to 90 degrees because CP is perpendicular to AQ. And we also know that MP is a common side. That means because those two triangles are congruent, their hypotenuse must be equal. So AP equals to PQ. The two red hypotenuse are equal. So to find PQ, we can just find AP. So now we're going to apply the trigo ratio for special angles. So we're going to look at the big triangle, triangle CAB first. So tangent 30 degrees, the blue angle as our reference angle, tangent of that blue 30 degrees is equals to the opposite, which is side AC, divided by side AB, the adjacent, which is 48 units. So tangent 30 degrees is a special angle, so it will give us 1 over root 3. So the length of AC is equals to 48 divided by root 3, which will give us 16 root 3. Now let's turn our attention to the smaller right-angled triangle, triangle CAP. Now in this smaller right-angled triangle, we can use the yellow 30 degrees as our reference angle. So tangent of that yellow 30 degrees is equals to the opposite AP divided by the adjacent AC, which we have just found to be 16 root 3. So once again, tangent 30 degrees is the same as 1 over root 3. We can conclude that the length of line segment AP is 16. Therefore, the side that we want to find PQ is also equals to 16. And that's our final answer. Moving on to question 12. In the figure, point O is the center of the circle, AD and BC intersect at point E, angle AEB is equals to 70 degrees, and angle AOB is equals to 62 degrees. Find the value of angle OCD. Pause the video here and give this question a good try. So question 12 is a circle properties question. The first thing we can do is we can find a vertically opposite pair. So angle CED is vertically opposite to angle AEB, both marked in yellow. So angle CED is also equals to 70 degrees. Next, we have angle at center is 2 times angle at the circumference, labeled in orange. So the angle at center, angle AOC, is equals to 2x. It is 2 times the angle at the circumference, angle ADC, which I've labeled in orange as x. Next, we can use the base angles of an isosceles triangle. Now we note that triangle OBC is isosceles because OB and OC are both the radius of the circle. So the base angle, the green angle, is equals to 180 degrees minus 62 minus 2x divided by 2. So we can simplify that to be equals to 118 degrees minus 2x over 2, and also can further simplify that as 59 degrees minus x. Now we can use the sum of angles in a triangle, and specifically triangle ECD. Now, this allows us to find angle OCD, the red angle that we want to find. So it's equals to 180 degrees minus away the yellow angle, the orange angle, and the green angle. So the red angle we want to find is equals to 180 degrees minus the yellow angle, which is 70 degrees, minus away the orange angle, which is x, and the green angle, which is 59 degrees minus x. And while we do not know what x is, the nice thing is that when we expand this and simplify this expression, we will get 51 degrees because all the x will cancel away. So our final answer for angle OCD is 51 degrees. Question 13. Find the value of 4 cosine 43 degrees divided by sine 73 degrees minus 12 sine 43 degrees divided by root 3 sine of 253 degrees. Pause the video here and give this question a good try. So for question 13, we need a few things. We need to know our trigo identities, particularly how to deal with trigo ratios of a third quadrant angle. We need to know our trigo ratio for special angles, and we need to know our addition angle formula. The first thing we can do is we can convert sine 253 degrees into negative sine 73 degrees. This is because 253 degrees is a third quadrant angle, so it's equals to negative sine of the principal value in the first quadrant, which is 73 degrees. We can also convert 12 into 4 times root 3 times root 3. So the root 3 in the numerator and the denominator will cancel out. Then we can add the two fractions because they now have the same denominator. It will become 4 cosine 43 degrees plus 4 root 3 sine 43 degrees divided by sine 73 degrees. Now we can also split the sine 73 degrees. 73 degrees is the same as 30 degrees plus 43 degrees. So, and we want that because the numerator has 43 degrees and 30 degrees is a special angle. So we can apply the addition angle formula to expand sine 30 plus 43. This will give us sine 30 degrees cos 43 degrees plus cos 30 degrees sine 43 degrees in the denominator. And sine 30 is equals to half. Cosine 30 degrees is root 3 over 2. This is our trigo ratio for special angles. So let's sub that in. And you can see that we can factorize a 4 from the numerator. We can also factorize a half from the denominator. And what's left? In our bracket, in both the numerator and the denominator, we have the same factor, cosine 43 degrees plus root 3 sine 43 degrees. So let's cancel that away. So the answer is just 4 divided by half, which is 8. Question 14. If x squared over 5 plus y squared over 7 is equals to 1, find the largest possible value of x plus y whole thing squared. Pause the video here and give this question a good try. So to tackle question 14, we can represent the equation x squared over 5 plus y squared over 7 equals to 1 as the equation of an ellipse. So this is its graphical form. And we want the largest possible value of x plus y squared. We can just find the largest possible value of x plus y. So let's assume x plus y equals to some value k. If we draw the line x plus y equals to k, that's actually this red downward sloping line with a gradient of -1. And we can make the y the subject, so y equals to k minus x, and solve using simultaneous equation. We sub that into the original equation. It will give us x squared over 5 plus k minus x squared over 7 equals to 1. we expand the k minus x squared and we multiply by 35 throughout, and we can simplify this equation to get 12x squared minus 10kx plus 5k squared minus 35 equals to 0. Now, if we want the largest possible value for k, this red line needs to be pushed as outwards as possible from the blue ellipse, either upwards or downwards. So what happens is that this red line becomes tangent to the blue ellipse. So if it's tangent, then the discriminant b squared minus 4ac is equals to 0. So b is equals to minus 10k. So b squared is 100k squared, a is 12, and c is 5k squared minus 35. We simplify this, we'll get k equals to plus or minus 12. The plus 12 is shown with this red line, and the negative 12 is actually this other red line. But we don't want k. The thing that we want is x plus y squared, which will be k squared. So the final answer is 144. Question 15. Find the coefficient of x to the power of 6 in the expansion of 1 plus x plus 2x squared whole thing to the power of 7. Pause the video here and give this question a good try. So question 15 is a trinomial expansion problem, and we're not going to solve the trinomial expansion. Instead, we're going to change this into a binomial problem by substituting a equals to x bracket 1 plus 2x. This will change the expansion into that of 1 plus a to the power of 7. Now, it's not difficult to use binomial expansion to expand all 8 terms of this expansion. However, it would not be useful to do all 8 terms. You will see that some terms are trivially useless, like 1 plus 7a. Let me go to the first non-trivial term, which is 21a squared. 21a squared, if I substitute back a equals to x bracket 1 plus 2x, I will get 21x plus 2x squared whole thing to the power of 2. But you'll see that if I expand this, the highest power is only x to the power of 4. So even 21a squared is of no use to me. It doesn't contribute any x to the power of 6. So let's look at the next term, 35a cubed. If I expand this, I sub in the a equals to x bracket 1 plus 2x, I'll get 35x cubed bracket 1 plus 2x to the power of 3. Now, since I have x cubed outside, I need another x cubed to form an x to the power of 6. So the coefficient of x cubed in the expansion of 1 plus 2x cubed is actually the last term, which is 2 cubed times x cubed. So the coefficient that is contributed from 35a cubed is actually 35 times 2 cubed. So let me put that in the answer space below. Next, let's look at 35a to the power of 4. If I substitute a equals to x bracket 1 plus 2x, I'll have 35x to the power of 4 bracket 1 plus 2x to the power of 4. So now I need the coefficient of x squared from the binomial expansion of 1 plus 2x to the power of 4. And that will be the third term, which is actually 4 choose 2 times 2 squared times x squared. So altogether, this 35a to the power of 4 contributes a coefficient of 35 times 6 times 2 squared. 6 comes from 4 choose 2. Next, let's look at 21a to the power of 5. If I sub in the a again, I'll get 21x to the power of 5 bracket 1 plus 2x to the power of 5. And I need the coefficient of x from the binomial expansion, which is 5 choose 1 times 2. So altogether, this term contributes a coefficient of 21 times 5 times 2. And for the last one, 7a to the power of 6, this one I have a 7x to the power of 6 bracket 1 plus 2x to the power of 6. Oh, I need the constant term from the binomial expansion, which is just 1. So this contributes a coefficient of 7. A to the power of 7, I don't have to look at it because the smallest power is already x to the power of 7. It will not contribute any coefficients to x to the power of 6. So the final answer is just adding up all the coefficients we've gathered from the various terms, and it's just 1337. It's the final answer. Moving on to question 16. Suppose we're given the equation that bracket 3x minus y bracket square plus square root of x plus 38 plus 14 root of x minus 11 plus the modulus of z plus x minus y equals to 7. We want to find the value of modulus of x plus y plus z. So could you pause the video here and give this question a good try? So to solve this question, I'm going to divide this in function on the left-hand side into three separate functions: the square, the surd, and the modulus. And I want you to also recall that all squares are non-negative. The smallest a square can be is 0. Surds are also non-negative, and modulus are non-negative as well. So the smallest each of these three boxes can be is 0. And let's first examine the surd highlighted in yellow. Let's take the case, can x be less than 11? Nope. If x is less than 11, then we'll be taking square root of a negative number. That would be undefined. But could x be more than 11? Well, that's not possible either. Otherwise, I'll be taking square root of 11 plus 38 plus a positive term. And that would be more than 7. And if the yellow term is more than 7, and the green and blue terms are non-negative, the left-hand side surely is bigger than 7, and it cannot be equals to 7. So x cannot be bigger than 11. Therefore, x has to be exactly 11. This also tells me that the green term and the blue term will both be 0. So let's sub in x equals to 11 first. I will get bracket 33 minus y squared, and I replace the surd with 7, and the modulus would be modulus of z plus 11 minus y. Now the 7 on both sides can easily cancel, but let's particularly solve for the y in the square term first. So this 33 minus y has to be 0, and the z minus 11, z plus 11 minus y also has to be 0. So this is only possible if y is exactly equals to 33, and that will make z equals to 22 as well. So if we sub this in into modulus of x plus y plus z, we will get modulus of 11 plus 33 plus 22, which is exactly 66. And that's our final answer. Question 17. Given that x, y, z are real numbers and they satisfy the following equations, equation 1 that x plus y plus z equals to 60, and equation 2 xy minus z squared equals to 900, find the maximum possible value of the modulus of z. Pause the video here and give this question a good try. So to solve this question, we're going to pretend that x and y are the roots of some quadratic equation that we are going to find. And we can find this quadratic equation because we have the sum of roots. X plus y is equals to 60 minus z. Next, we can also find the product of roots. X times y is equals to 900 plus z squared. So if we use Beate's formula, that x squared minus the sum of roots times x plus alpha beta, the product of roots is equals to 0, we can sub in the sum of roots to be 60 minus z and the product of roots to be 900 plus z squared in this. And of course, we're not going to use x as the variable now that x is one of our unknowns. So we're going to use the variable p. So our equation is p squared minus 60 minus z times p plus 900 plus z squared equals to 0. So what can we do from here? Well, we know that the coefficients are real. We also know that the roots are real. So what can we do if we know that this equation has two real roots? Well, we can find the discriminant. The discriminant, the b squared minus 4ac, must be positive, or at least greater than or equal to 0. So we can sub in b equals to 60 minus z, and a equals to 1, and c equals to 900 plus z squared, and solve for this inequality. So this will give us negative z bracket 40 plus z greater than or equals to 0 when we fully simplify it. We can draw the quadratic for z. It will look like this. It has a root at negative 40 and 0, so z must vary between 0 and negative 40. Next, we can find, since we know the smallest possible value of z is negative 40, then the maximum possible value of modulus z will be positive 40. And that's our final answer. In question 18, we have a very scary looking question. We want to evaluate the sum from k equals to 1 to k equals to 16 of log base 2 of bracket square root of sine square k pi over 8 plus 1 minus sine k pi over 8. Pause the video here and give this scary looking question a try. And while this sum may look scary, actually it's not very scary at all. Let's look at a few cases where it is very easy to evaluate. Let's take the case of k equals to 8. If I sub in k equals to 8, then actually I'm taking sine square of pi inside the square root. And this is very easy to evaluate because sine of pi is 0. This will simplify into log base 2 of square root of 1 minus 0, which is just 0 because it's log base 2 of 1. Similarly, if I take k equals to 16, I'm taking log base 2 of bracket, a lot of stuff, but pay attention to the sine square. I'm taking sine square of 2 pi and I'm taking a sine of 2 pi. Sine of 2 pi is also 0. So there's nothing here to be frightened of. It will also become 0. So the two trivial cases are actually k equals to 8 and k equals to 16. They evaluate to nothing. We got rid of 2 terms. What about the remaining 14 terms? So what we can do is we can pair them up and kill them off. So we're going to pair k equals to 1 with k equals to 15. So I have this horribly large equation here. I'm not going to read it out. But the important thing is that pi over 8 and 15 pi over 8 are related. They both have the same principal value. One is a first quadrant angle, one is a fourth quadrant angle. So we can use the formula sine bracket 2 pi minus theta equals to negative sine theta. So sine of a fourth quadrant angle is equals to negative sine of a first quadrant angle, the principal value. This changes sine of 15 pi over 8 into negative sine pi over 8. That's why there is a plus sign highlighted in red there. The sign has changed. And we can add these two logs together using the product law. So it will just become this. And we can expand the brackets because what we have is a minus b times a plus b situation. So it's going to become log base 2 of a square minus a b square. So if we simplify it, we get this. And lo and behold, we get a sine square pi over 8 plus 1 minus a sine square pi over 8. So the sine square pi over 8 will cancel. And all we're left with is log base 2 of 1, which is just 0. So I'm not going to show you every pair that adds up to 0. Let me just show you one more pair. For example, k equals to 5 and k equals to 11. If we add these two terms together, you'll see that 5 pi over 8 is connected to 11 pi over 8. Sine 11 pi over 8 is equals to negative sine 5 pi over 8. One is a second quadrant angle, one is a third quadrant angle. So I can change sine 11 pi over 8 into negative sine 5 pi over 8. Same thing again, there will be a plus. I can use the product law again to combine the two logs together. I can expand the brackets. This is a minus b times a plus b situation again. I'll get the a square minus b square, which will just give me a sine square 5 pi over 8, which will also subtract and cancel away the negative sine square 5 pi over 8. And I'll get a log base 2 of 1, which is still 0. So altogether, there's going to be a lot of pairs. I'm just going to summarize it here. The first term and the 15th term, that means k equals to 1 and k equals to 15 cancel. K equals to 2 and k equals to 14 will also cancel with one another. You can go and try for any of these pairs and check out that they all cancel. And earlier at the start, I've also told you that where k equals to 8 and k equals to 16, they are both equals to 0. So altogether, every term will add up to 0, so the final answer will be 0. Question 19. Given that a and b are positive real numbers and that a is bigger than b, suppose there exists a real number x such that the log base 2 of ax times log base 2 of bx plus 25 is equals to 0. Find the minimum possible value of a over b. Pause the video here and give this question a good try. So to solve this problem, maybe we can first change this log problem into an indice problem, which is easier to manage. So what I can do is I can let log base 2 of ax equals to k and log base 2 bx equals to negative 25 over k. That way, if I multiply these two logs together, the k's will cancel out and I'll get negative 25. which will add to the positive 25 to give us 0. Now I can change each of these into an index problem. So ax will be equals to 2 to the power of k, and bx will be equals to 2 to the power of negative 25 over k. I can divide these two equations with one another. So on the left-hand side, I'll take ax divided by bx. That will give me what I want, which is a over b. And on the right-hand side, I'll get 2 to the power of k divided by 2 to the power of negative 25 over k. So I'll get 2 to the power of k minus 25 over k. That's why I get a positive 25 over k. So the minimum possible value of a over b will be the minimum possible value of that power k plus 25 over k. And I can find that minimum possible value by differentiating. If I differentiate k plus 25 over k with respect to k, I'll get 1 minus 25 over k squared. And since I want the minimum, the differential has to be 0, so k has to be plus or minus 5. Now the answer will be k equals to 5. Why can't it be minus 5? It's because a is greater than b. If k is negative 5, then a would be less than b. So if I sub in k equals to positive 5, a over b will be equals to 2 to the power of 5 plus 5, which will be 1024. It's also not difficult for you to sub in some other values of k to verify that any other values of k will give me a 2 to the power of something bigger than 10. Okay, so this is our final answer. Question 20. The figure below shows a rectangle ABCD such that AC equals to 20 cm. Let P be a point on side CD such that BP is perpendicular to AC. Find the area of the rectangle ABCD if BP is equals to 15 cm. Pause the video here and give this question a good try. So to tackle this question, we first recognize that we have a pair of similar triangles. This can be shown using the AA test because you have two pairs of alternate angles and one pair of vertically opposite angles. So I'm also going to mark the intersection of line AC and PB to be point M. That way I can state that because they are similar triangles, BM can be K times the length of MP. And by the ratio of corresponding sides of similar triangles, AM will also be K times of the length MC. So with this, I can form two equations. I can say that A plus KA, which is the length of BP, is equals to 15. So equation 1 will be 1 plus K times of A equals to 15. And similarly, using the length of AC, I can show that 1 plus K times of B is equals to 20. Next, I'll take equation 1 divide by equation 2. That way my k will cancel away and I'll be left with a over b equals to 3/4. Now I can let a equals to be 3x and b to be equals to 4x. Now we can apply Pythagoras theorem to find the hypotenuse for the blue and green triangle. We will get 5x and 25 minus 5x respectively. Next, we turn our attention to a different right-angled triangle. Let's look at triangle PCB, this blue triangle. We know that the hypotenuse is 15 and it has a side of 5x. We can use Pythagoras theorem to find the length of BC. We will get square root of 15 squared minus 5x squared. Next, we can turn our attention to a different right-angled triangle. Let's look at this orange triangle. We know that the hypotenuse is 20, the base is 25 minus 5x, and the height is square root of 15 squared minus 5x squared. This time when we apply Pythagoras theorem, we are forming an equation. We can simplify this equation. We will divide 5 squared throughout to get this, then further simplify this, and eventually the x squares will cancel, and we will get x equals to 1.8. Substituting x equals to 1.8 into the diagram, we'll see that the base of this rectangle is 16 and the height of this rectangle is 12. We can then work out the area of this rectangle. base times height will give us 192 as our final answer. Question 21. Find the smallest positive integer that is greater than the following expression. Bracket square root of 7 plus square root of 5 close bracket to the power of 4. Pause the video here and give this question a good try. Now to solve this problem, we're going to treat this as a binomial expansion problem. So what we have is something like a plus b to the power of 4, and that's going to give us a to the power of 4 plus 4a cubed b plus 6a squared b squared plus 4ab cubed plus b to the power of 4. So if we substitute a equals to root 7 and b equals to root 5, this is what we'll get. And notice that on the right-hand side, we can almost work that out, except that the second and the fourth term, they are surds. We'll need a calculator, which we don't have. Fortunately, what we could do is we can consider root 7 minus root 5 to the power of 4. Now we'll get almost the same expansion, except that the second and fourth term are now negative. So if we add these two equations together, on our left-hand side, we will get root 7 plus root 5 to the power of 4, plus root 7 minus root 5 to the power of 4. And on the right side, these are all numbers that we can evaluate manually. Now, note that root 7 minus root 5 is a number between 0 and 1. So if we raise that to the power of 4, it will still be a number between 0 and 1. And if we calculate the right-hand side, we get 568. That must mean that root 7 plus root 5 to the power of 4 has to be a number between 567 and 568. Therefore, the smallest positive integer greater than the expression given has to be 568, which is our final answer. Question 22. Find the number of non-congruent right-angled triangles such that the length of all their sides are integers and that the hypotenuse has a length of 65 cm. Pause the video here and give this question a good try. So to solve this problem, what we can first do is prime factorize 65. 65 is equals to 5 times 13. And 5 and 13 are very nice numbers because let's take, for example, 5. 5 is the hypotenuse of the infamous 3, 4, 5 triangle. We know that 3 squared plus 4 squared equals to 5 squared. And if we multiply by 13 squared throughout, this gives us a triangle with sides 39 and 52 and a hypotenuse of what we want, 65. Next, if we look at 13, well, 5 squared plus 12 squared equals to 13 squared. This is another famous right-angled triangle. Well, we can multiply throughout by 5 squared. This will give us 25 squared plus 60 squared equals to 65 squared. So that's another possible right-angled triangle with sides 25, 60, and a hypotenuse of 65. But are there any more? Are there any more triangles such that a squared plus b squared equals to 65 squared? Well, let's consider what will happen if we make a squared the subject. So a squared equals to 65 squared minus b squared. We can use the difference of square. This will give us 65 plus b times 65 minus b. And since a squared is a square, that must mean that the factors 65 plus b and 65 minus b must both be square numbers too. So let's call them x squared and y squared. And now, we know that y squared has to be a square number less than 65 because it's 65 minus b. So let's list out all the possibilities. It could be 64, 49, 36, all the way to 1. And if we think that y squared is 64, we can work out what is b. So 65 minus 1 gives us 64. So b would be 1. And that allows us to work out x squared, which would be 65 plus 1, which is 66. But that's not a viable answer because 66 is not a perfect square. The first such perfect square x squared would be 81. And that corresponds to a right-angled triangle with sides 63 and 16 because 63 squared plus 16 squared gives us 65 squared. And the only other possibility, if we look down the column for x squared, is 121. So these are the only two square numbers that we can find. So that will correspond to another right-angled triangle with sides 33 and 56. So 33 square plus 56 square also gives us 65 square. So all in all, we have 4 such triangles. Question 23. There are 6 couples, each comprising of a husband and a wife. Find the number of ways to divide the 6 couples into 3 teams such that each team has exactly 4 members and that the husband and the wife from the same couple are in different teams. Pause the video here and give this question a good try. So for this question, I'm going to use colored dots to represent the team members. So for the 12 team members, I've used 12 dots and I've color coded them blue, red, and green to represent the 3 different teams. Now, instead of taking married couples and dividing them into 3 teams, what I've done is that I have the 3 teams first and I'm going to marry the couples off. So if I marry a couple off, I'm going to draw a line between the 2 colored dots. So let's consider a possible case. Could it be possible that the 4 blue team members are married to the 4 red team members? Well, it's not, because if you look at the green team, they can't be married to one another. So there's a contradiction here. So let's consider another case. What if only 3 blue team members are married to 3 red team members? Well, again, we have a contradiction because the last blue team member is married to the green, the last red team member is married to the green, but there's still 2 green members left over. So that's not possible under the rules as well. So the only possibility is for the 2 blue team members to be married to 2 red, 2 blue married to 2 green, and 2 red married to 2 green. So this is the sort of the graph that represents the possible permutations that we need to consider. So now that we know that the graph looks like this, we need to count the possible permutations that fit this graph. So let's just pick one of the teams. Let's take the blue team, and we have 6 couples altogether. We need to choose 4 of the couples to form this blue team. So for example, I could pick couple ABCD or couple BCDE and couple CDEF. But out of these 4 couples, I need to choose 2 of them to be married to the red. So I need to multiply by 4, choose 2. Then by default, the other 2 couples will be married to the green team. And the next thing I need to consider is that I have not considered whether it's the husband or the wife in the blue team, or in the green team, or in the red team. So for each of the couples, I can swap them around. So the husband and the wife can switch place. And for each switch, that will be times 2. So altogether, I have to times 2 to the power of 6 for the 6 couples. Next, I need to consider the symmetries. Well, if I were to swap all the blue team members to the red team member and the red team members goes back to the blue team, actually there's no difference in the ordering. So I have to divide by 3 permutate 3 to make sure I don't double count any permutation. So if I take 6 choose 4 times 4 choose 2 times 2 to the power of 6 divided by 3 permutate 3, which is actually 3 factorial, I'm going to get 960, and that's our final answer. 24. The digit sum of a number is the sum of its digits. For example, the digit sum of the number 987 will be the sum 9 plus 8 plus 7, which is 24. Let A be the digit sum of 2020 to the power of 2021, and let B be the digit sum of A. Find the digit sum of B. Pause the video here and give this question a good try. So question 24, this is going to be a little hard, and we're going to need some modular arithmetic at the end. So if you're not familiar with that concept, you might want to fast forward to question 25. So let's begin. Step number 1, we're going to find an estimate of the upper bound of the digit sum for 2020 to the power of 2021. So what we're essentially doing is finding the length of this number, and we can do so by taking log base 10 of the number and add 1. But since I'm going to be taking a serious overestimate, that plus 1 doesn't really matter. Now, using the power law for logarithms, I can bring the power 2021 down as the coefficient. Next, we can use the change of base law to change it to base 2. So I get this fraction in red, log base 2 of 2020 divided by log base 2 of 10. Now, since we don't have a calculator, we can't evaluate log base 10 of 2020. We're going to take an estimate. So, and to make sure our estimate is an overestimate, I need to round the numerator up and I need to round the denominator down. So to do so, I need a power of 2 that is slightly larger than 2020 and a power of 2 that's slightly smaller than 10. And that would be 2048 and 8 respectively. That means that this fraction in red will be less than the fraction 11 over 3. And the digit sum, the entire length of this number will be less than 7,411 digits. These are all estimates. If you actually key it into a calculator, it would be 6,681 digits long. So our estimates of 7,411 is a pretty good one. Now that we know that the digit sum of A is 7,411 digits long, we could just assume that all the digits are 9. But we can do something better than that, because we know that 2020 ends with a 0. Therefore, if you raise that to the power of 2021, it's going to produce a number ending with 2021 zeros. And all these zeros won't count to the digit sum. Therefore, we can take 7,411 minus 2021 times 9. That tells us that A can be at most 48,510. Now, to find the digit sum of B, the upper bound, we can just look at the number A. What number smaller than 48,510 produces the largest digit sum? And that number is 47,999. So B can be at most 38. Then we have to do this one more time. What number smaller than 38 produces the largest digit sum? And that would be 38 itself. That will produce a digit sum of 11. Therefore, that would be the largest possible value for the digit sum of B. So at this point, if you don't know modular arithmetic, you could just guess a number between 1 and 11 and just hope for the best. If not, here comes the modular arithmetic part. So firstly, we need to recall the divisibility rules of 9. If a digit sum of a number is divisible by 9, the number itself will also be divisible by 9. It turns out that as an extension to this property, if the digit sum of a number leaves a remainder of 4 when divided by 9, that original number will also leave a remainder of 4 when divided by 9. So in modular arithmetic, we can write it this way. These four numbers, 2020 to the power of 2021, plus its digit sum A and its digit sum of A, which is B, and the digit sum of B, all these four numbers have the same remainder when divided by 9. So all we have to do is find the remainder when 2020 to the power of 2021 is divided by 9. We can start off simply by looking at 2020 itself without the power. So 2020 gives us a remainder of 4 when divided by 9. We can raise both sides to the power of 2021 using a modular arithmetic rule. They would still have the same remainder. Next, if we look at the powers of 4, there's a very interesting power of 4, which is 4 cubed. 4 cubed gives us a remainder of 1 when divided by 9. And if we raise both sides to the power of 673, we can see that 4 to the power of 2019, which is 4 cubed to the power of 673, will give us a remainder of 1 when divided by 9. And 4 to the power of 2019 is a power of 4 that is closest to 4 to the power of 2021. So if we want the remainder of 2020 to the power of 2021 divided by 9, that would be the same as 4 squared divided by 9, because we can subtract away a power of 2019 from 2021. And 4 squared is 16. 16 gives us a remainder of 7 when divided by 9. That means that within the possible numbers for the digit sum of B between 1 and 11, is there a number with the same remainder? So a remainder of 7 when divided by 9. Yes, there is. That would be the number 7 itself. So 7 is our final answer. Last but not least, we have question 25. Now we have two examples given here. 40, the number can be expressed as 2 cubed times 5, is a positive divisor of 1440, but it's a product of 4 prime numbers. 48 is another positive divisor of 1440 and is a product of 5 prime numbers, which is 2 to the power 4 times 3. We want in this question to find the sum of all positive divisors of 1440 that are the products of an odd number of prime numbers. That means 40 isn't good because 4 is an even number, but 48 is a number that we want to find because it comprises of 5, an odd number of prime numbers. So we want the sum of all such divisors. So pause the video here, give this question a good try. So it turns out that for question 25, it is not that hard to actually brute force this. First, we need to prime factorize 1440. That gives us 2 to the power 5 times 3 squared times 5. And we want to look at divisors that only form one prime number, that's formed by only one prime number. There's only 3 numbers, 2, 3, and 5. Now we want divisors that consist of 3 prime numbers. We can methodically list them starting from numbers that has 3 factors of 2. That's just 2 cubed. Numbers that have 2 factors of 2, that will be 2 squared times 3 or 2 squared times 5. Numbers that only have 1 factor of 2 will be 2 times 3 times 5 or 2 times 3 squared. Numbers that do not have a factor of 2, there's only one possibility, it's just 3 squared times 5. So we can do this kind of methodical listing for divisors consisting of 5 primes, divisors consisting of 7 primes, and for 9 primes, we don't have to do it anymore since this number only has 8 prime numbers that form it. So if we tally up all these numbers together, that gives us a total of 2,163. And that comes to the end of SMO 2020. So if there are any errors that you've spotted or anything you're not quite sure of arising from the video, you could post it in the comment section below. Next up, I hope to make a similar walkthrough for the junior section for the 2020 Olympiad. I hope that these videos will be helpful for your Olympiad preparation. Do like the video and subscribe to the channel for more math content in the future. Lastly, thank you for your kind attention and have a great day of learning.